So good afternoon everyone and welcome to this lecture. We are into lecture number 3 on work power energy, and in the
Yes.
last class we had seen the work energy theorem. Yes or no?
Yes, sir.
We had seen how we can use this work energy theorem. This work energy theorem is nothing but it simply states that the work done by all forces is
All
equal to.
forces is change in kinetic energy.
We can apply these. We can apply this wherever we want, wherever we have work done. If we have one force, if we have many force, we find out the work done by all forces, and that work done actually is, we get this work done in the form of change in kinetic energy. Now we have done work done by forces. Now these forces, when we talk about these forces, we can actually think of these forces that we come across. This can be categorized into two ways. There are different ways in which you can categorize force. One of these ways is when we call them as
Non-conservative.
conservative and non-conservative forces. So we must also look at what do you mean by these conservative and non-conservative forces. Let us start with some examples. Maybe that will give us more insight. Do you know of any conservative force? Any examples of conservative force?
Gravitational force, sir.
Gravitational force is conservative, spring force is conservative, electrostatic force is conservative. These are the three different types of conservative forces that we will come across: gravitational force, electrostatic force, spring force. When we talk about non-conservative force, any resistive force, friction, air drag, all these are non-conservative forces. Now, what do you mean by this conservative and non-conservative forces? There are two things that we must remember about these conservative or these non-conservative forces. Let us first talk about these conservative forces. Conservative forces like gravity, gravitational force, spring force, or electrostatic force. What is the first thing that we must remember about this conservative force? Work done by or against this conservative force does not depend on work done by this force does not depend on path. It does not depend on path from where to where you are moving, in which path you are moving. It does not depend on the path in which that work is done. I mean, it only depends on from where to where you have shifted the body. It does not depend on how you have shifted the body. Do we understand this?
Yes, sir.
That is the first thing that you must remember about conservative forces. If I can show you a diagram, this is how you can understand these conservative forces. I hope you can see this diagram. If you have any conservative force and if I move a body from point A to point B by path number 1 or path number 2 or path number 3, the work done by this conservative force through any of these paths, whether it is path number 1 or it is path number 2 or it is path number 3, they are all equal. In path number 1, this is the work done F dot dl over path 1. In part number 2, again I write it as F dot dl for part 2. Then for path number 3, I also write it as F dot dl for path number 3. That means I can say that this line integral, this integral is basically F dot dl or F dot dr. This is the work done. We also call it line integral f dot dl. F dot dl is line integral. F dot dA will be surface integral. F dot dB will be volume integral. Okay, this line integral does not depend on path. It is independent of path. So if you have a force such as gravitational force or spring force or electrostatic force, the work done by this force does not depend on path.
Path.
You go on any path, the work done would be same. Do we understand this?
Yes, sir.
The same thing we can say in a different way. If I move in a closed loop, work done by conservative forces or against conservative forces in a closed loop, in a closed path, in a closed loop is always equal to 0. What does that mean? If I take an example, if I bring a body from ground, if I bring a body of mass m from ground and I bring it to this point, let us say A, I raise it to a height h. Now, if I think about work done by gravity from from B, this point B to point A, when I'm moving up, gravity is downwards. Work done by gravity is negative. When this body moves from A to B, the work done by gravity will be positive. The net work done by gravity from B to A and A to B will be 0. Yes or no?
Yes, sir.
That is what we mean when we say work done by or against any conservative force in a closed path is 0. Do we understand this?
Yes, sir.
In any closed path, if you find out the work done, why it is 0? Because your initial and final positions are 0. So it is something like displacement. Your initial position and your final position is the same. Therefore, there is no work done. You can understand it in this way. Do we understand this? So this is how we write it. The line integral, which is the work done over a closed loop or path, is 0. If I start from this point and come back to this point, your displacement is 0. Your work done is 0. But again, this is only valid if the force
Conservative.
is conservative. Do we understand this concept?
Yes, sir.
Okay, we can take the example of a conservative force, and the best example of a conservative force is which one? Best example of a conservative force
Gravitation.
is gravitational force, and we can understand this by this simple example. If I bring a block from point A to point B, if I raise it vertically upwards, straight vertically upwards, the work done by gravity is downwards and displacement is upwards. The work done by gravity will be minus mgh. Yes or no?
Yes, sir.
Even if I take it at any angle, if I take it along the slope, the work done by gravity still is minus mgh.
Minus mgh.
So this is an example. If I take it like this also, the work done by gravity will be minus mgh. It does not depend on path. If I take it like this also, the work done by gravity will be minus mgh. It does not depend on path. So to find out the work done by gravity, you just see how much is the height it has moved and how much is the weight of the body. If it is moving downwards, work done would be positive. If it is moving upwards, work done would be negative. Do we
Negative.
understand this? Yes or
Yes,
no? No,
sir.
yes. This
Yes,
is
sir.
what we mean by conservative forces. And the other forces, then the other force that we have is known as
Non-conservative
non-conservative
force.
force. So non-conservative force is just the opposite of it. Non-conservative force. The example of non-conservative forces are
Resistive force.
all the resistive
Force.
forces, friction, and all those are non-conservative force. So just reverse the things. Work done depends on,
Path.
it depends on path. If I go in one path, work done would be different. If I go in other path, the work done would be
Would be
different.
different.
Work done in a closed loop will not be equal to 0. Do we understand this? So if I move a block in a round circle, the work done by gravity is zero, but the work done by friction is not zero. Do we understand this? Yes or no? Do we understand this? Yes or no? Yes or no? We can take the example of this simple body. The frictional force is mu mg. Yes or no? If I move this body from point A to point B, what is the work done from point A to point B? Work done by frictional force from point A to point B. How much will be the work done? It will be minus mu mg into s. Yes or no? What will be the work done? I cannot hear you, beta. When I bring it back from B to A, when I bring it back from B to A, frictional force will again act in the backward direction, but now the body is moving like this and friction force will be acting like this. So the friction force ka work done will be still minus mu mgs. If I say the total work done by friction force from A to B to A, it is not coming as 0, it is coming as minus 2 mgs. Do we understand this? So that is what we mean by conservative and we mean by non-conservative forces. Remember these. We will come across both of these forces, sometimes conservative, sometimes non-conservative. We must remember that for conservative forces, work done does not depend on path. For non-conservative forces, it depends on path. Do we understand this? Okay, let us solve this question. Question number 1, you don't have to write the question, just look at the question and try to answer it. Call this question number 1. If W1, W2, and W3 are represent the work done in moving a particle from A to B along 3 different paths in the gravitational field of a point mass m, what would be the correct relation? What would be the correct relation?
Sir.
Yes, the answer is?
B.
The answer is B. Gravitational field is a conservative field. Gravitational force is a conservative force. Work done by or against any conservative force will be independent of the path. Do we understand this? Yes or no?
Yes, sir.
Okay. Now, this is all about conservative forces that we must remember. So the correct option here is B. Remember, whenever we have conservative forces, we can understand this work done by conservative forces in a different way. Now we understand that this work done by conservative forces does not depend on path, and here now comes the next heading for this chapter. And the next heading for this chapter is potential energy, or I should say potential energy difference. Now, what all things that you must remember or do you know about potential energy? Yes. What do you understand by the term potential energy?
Energy possessed by the body due to virtue of its position, sir.
Energy possessed by a body by virtue of its position. Yes, it is correct. Energy possessed by a body energy possessed by a body by virtue of its position where? Where? In a conservative field. So if a body is present in a conservative field, what do you mean by conservative field? Gravitational field is a conservative field.
Yes, sir.
Electrostatic field is a conservative field. If you have a gravitational field, for example, where I am sitting or where you are sitting, do we have a gravitational field here?
Yes, sir.
Created by whom or what?
Sir, come again.
Are we sitting in a gravitational field? Are we experiencing a gravitational field where you are sitting or where I am sitting? Are we experiencing a gravitational field?
Yes, sir.
Created by what? Who is creating this gravitational field? Earth, because of its mass, is creating this gravitational field.
Yes, sir.
Therefore, this body, which has got a mass, if I place it here, because now this body has a mass and it is present in a gravitational field, it possesses energy because it can do work. This energy possessed by a body, when it is present in a conservative field, is known as potential
Potential
energy.
energy.
So you'll have three types of potential energy that you will encounter: gravitational potential energy, electrostatic potential energy, spring potential energy. These are the three different types of potential energies that we will encounter. Do we understand this? Yes or no?
Yes, sir.
Now, this potential energy, since we have already mentioned that it only comes because of conservative field, this is only associated with a conservative force or a conservative field. This potential energy is always associated with conservative force
Conservative force.
or a conservative field. Now, remember this potential energy that we are studying. We've just created this concept to understand a conservative field or to probably understand this conservative what work this conservative force does in a conservative field. Now, how do we find this potential energy? Now, remember this absolute value of potential energy is not defined. We don't define the definition when we talk about potential energy. The absolute value is not defined. In fact, absolute value of nothing is defined. The mass of this block or this phone is 300 grams. It is defined in terms of grams. Similarly, this potential energy की absolute value is not defined. Then what is defined? Only the difference or change in potential energy is defined. Only the change in potential energy is defined. What do you mean by change? For example, I have this body at point A and I move this to point B. From A to B, I am moving this body. Potential energy if at A, if I call it as A. Potential energy at B, if I call it as B. So what is the change in potential energy? When I move this body from A to B, what is the change in potential energy? Change, when I say change is
Final
all,
minus initial.
so it will be UB
B minus UA.
minus UA. So this change in potential energy is defined, and how it is defined? It is negative of work done by the force, conservative force, from A to B. So I'm moving the body from A to B. The change in potential energy is negative of the work done by the conservative force. Is negative of the work done by conservative force. Do we understand this? That
Yes.
is how change in any potential energy is defined. Do we understand this?
Yes, sir.
Now, if you can find a point whose potential energy can be taken as zero, if you can find a point whose potential energy is taken as zero, then with respect to that point, you can define the potential energy of other bodies. Yes or no?
Yes, sir.
In most of the cases, what is done is at infinity, potential energy is taken as zero. At infinity, the potential energy is taken as zero. So, if potential energy at infinity is taken as zero, then I can define potential energy at B as negative of work done by conservative force in moving the object from infinity to point B. Do we understand this? Do we understand this?
Yes,
So
sir.
basically, I have taken one point which is infinity as zero. If I take this one point as infinity at zero, then I can define the potential energy of all the other points. Now, when we are going to do questions, it may not be possible right now for us to take point at infinity to be zero. So what are we going to do? Whenever we are going to do any question, we are going to encounter in this year, we are going to encounter two types of potential energies. The first one would be gravitational potential
Gravitational
energy.
potential energy.
For the second one would be spring potential energy.
Spring
So what do
potential.
we do? For example, whenever we deal with any question on gravitational potential energy, we can take the gravitational potential energy of the lowest point. That is what I do. Gravitational potential energy of the
Has to
lowest
be
point,
zero.
if you take it as zero, most
Yes.
of the cases, the lowest point is ground, unless until the question is otherwise. So if I take the gravitational potential energy of this point or ground as zero, and then I have a block of mass m at a height h from this block, from a height h above this ground, then I can take the gravitational potential energy of this point as, or this body as, plus mg h.
H.
Do we understand this?
Yes, sir.
Since infinity is very far off and we don't know what happens at infinity, so in our discussion for this particular chapter, if you take the energy of ground as zero, anything above ground will have positive potential energy, and anything below ground, if there was anything below ground, so anything above ground will have positive potential energy, and anything below it will have, if I have a mass here below ground at a depth d, because this depth, then I can call the gravitational potential energy of this part minus.
Minus mgb.
Do we understand this?
Yes, sir.
Okay. Then we might encounter the case of spring. we might encounter the case of spring and a block attached to the spring. The spring would have a spring constant K. This is example number 2. Now, you will have some natural length of the spring. This L0 is the natural length of the spring. Do we understand this?
Yes, sir.
At this natural length of the spring, we can take what? The spring potential energy as 0. We can take for a spring, we can take when the spring is unstretched, when the spring is not stretched, when the spring is at its natural length, we can take the spring potential energy to be 0. If I take it that way, then if I extend it by an amount x, how much energy it will have if I extend the spring by an amount x? If I extend the spring by an amount x, what will be the spring potential energy that it has? It will be now equal to, no one knows? Plus half k x square, where k is the spring constant. Have you heard about spring constant? Yes or no?
Yes, sir.
Where k is the spring constant and x is the extension in the spring. On the other hand, if I compress it by an amount x, if I compress it, oh, sorry, wrong diagram. No, correct diagram. L is there. Sorry. If I compress it by an amount x, then what will be my spring potential energy at this point when it is compressed by an amount x? When it is at natural length,
Minus.
spring potential energy is 0. When it is extended, the spring potential energy is plus half kx square. If it is compressed, then
Minus half kx.
no, it is still plus half kx square.
Okay, sir.
So the spring potential energy is not negative at any point. It can only be 0 or it can only be positive. I'll give you 2 minutes to note this down.
Done, sir. Done, sir.
Okay. So we have understood the concept of potential energy. Now remember, potential energy is only associated with
Conservative.
conservative forces. Now you might encounter certain cases, for example, this one. Note it down as an example. What is the potential energy of this? What is the potential energy of this rod? Let us say, for an example, if I take the potential energy of ground as 0, what can I take the gravitational potential energy of this rod? Any idea? So how do I find the gravitational energy of this rod? I find out this center, and its center is at a height how much?
L/2.
And if I calculate its gravitational potential energy, it will come same as mg into L by 2, which is equal to, considering that it is not a rod, it is a point, and the center point, whatever energy the center point has, that is the gravitational potential energy of the entire system. Do we understand this?
Yes, sir.
All these things that we are doing are potential questions. I hope you understand them.
Yes, sir.
Okay, these are going to come as questions. Now, if I ask you, what will be the gravitational potential energy of this one? At ground, the gravitational potential energy is taken as 0. Yes,
mg/2 sin theta, sir.
mgl by 2 sine theta. That is correct. How did you get it? You actually locate the center of this
Yes, sir.
and you just find the height of this center from ground, and that will be mgl by 2
L/2
plus mgl by 2
plus.
sine theta. Do we understand this?
Yes,
Actually,
sir.
what we are locating is not actually the center. It is known as COM. Have you heard about COM?
Center of mass.
Trying to locate the center of mass of that body, and that is how this point, the center of mass, becomes so important, because it comes so many times in so many different ways. Now, if I had this, what will be the gravitational potential energy of this? This could be a sphere of mass m and radius r. This could be a spherical shell of mass m and radius r. This could be a ring of mass m and radius r. This could be a disk of mass m and radius r. All these things are same. This could be a cylinder of mass m and radius r. Everything is similar. If I take the gravitational potential energy of ground as 0, what is the gravitational potential energy of this? This is ground. Yes. Ma?
mgr, sir.
We just locate its center of mass. Its center of mass is here. The distance from the height of the center of mass is r. So the gravitational potential energy of this ring or
Yes,
disk or
sir.
sphere or shell can be taken as this one. What about this one? What will be the gravitational potential energy of this chain? The chain has a mass m, and it is put on a semicircular or cylinder. This is ground. The gravitational potential energy of this ground is taken as 0. What is the gravitational potential energy of this thing? Now remember, for a semi circle or hemisphere or whatever it is, The center of mass is located at a height of 2r by pi. So the gravitational potential energy of this rod will be mg into 2r by pi. Do we understand this?
Yes, sir.
Please note it down. Have you noted it down?
Yes, sir. Done. Sir.
These are some of the important points that you must remember about potential energy. We have already discussed this point. I just got it, so I just took them down point wise. Point number one, it only defined for conservative forces. Do we understand this? Potential energy can be positive, negative, depending on the choice of the reference frame where you are taking your zero. If you are taking your zero at ground, everything above ground is positive, everything below ground is negative. If you are taking it below ground, everything below that point will be negative and everything above that point will be positive. So it depends on the reference frame. Do we understand this?
Yes, sir.
Now, potential energy, the absolute value depends on reference frame, but the change in potential energy is independent. Do you
Dependent.
understand this? That is why change in potential energy is defined. Potential energy is a property of a system. If you change anything in the system, when I move this mass from here to here, actually I am changing the system, and that is why the energy is changing. Do we understand this?
Yes, sir.
It does not depend on path. Everyone understand this one, right?
Yes, sir.
Okay. Give you 2 minutes to note this down.
Done, sir.
Okay, then here comes a question for you. Find out the work done by an external agent to slowly hang the lower end of the rod of the chain to the peg. So this is the lower end of the chain, and this is what you can see, a peg, a nail. I have to hold the lower end, and put it at the top. What is the work done by external agent? I'll give you 2 minutes to do this. Shall I do it or are you trying?
mgl by 4, sir.
mgl by 4. That is correct. How did you get it? mgl by 4 is absolutely correct. How did you get it?
Potential energy, sir.
What potential energy, sir? So,
Change in
just tell me, tell me.
change in potential energy, sir.
Okay. So let me do this. Now I have to, some external agent will have to work on this chain and will have to bring it up. Now what I'm going to do is I'm going to apply this work energy theorem. What does this work energy theorem says? Work done by all
Work done
forces
by all
equal
forces
to.
is change in kinetic energy.
Now whenever it says slowly hang, that means the change in kinetic energy is to hang it slowly. What will be the change in kinetic energy? Whenever someone says it is done slowly, that means the change in kinetic energy is
0.
0. Now work done by all forces is equal to 0. Now what are the forces acting on this? What are the forces acting on this chain? One force is obviously the force which is here, but it is not doing any work because it is hanging. The point of application of force is not moving. The only two forces which are working here is work done by gravity plus work done by external agent.
Force.
That must be equal to. That means your work done by external agent will be negative of work done by gravity. Do we understand this?
Yes, sir.
Now work done by gravity can be written as negative of change in potential energy, right? U final minus U initial. Yes or no?
Yes, sir.
Now this is the final position and this is the initial position. Yes or no?
Yes, sir.
Now what is the energy in the initial position? If I take this point as 0 because this point is same for both of them. If I take this point as 0, what is the initial energy? Ui. It will be minus mg into L by 2.
Yes, sir.
And why minus? Because I've taken topmost point as 0, so everything is negative. What about the final energy? U final minus mg into L by 4. Yes or no? I put these values here. U final is this one. U initial is this one. Do we understand this?
Yes, sir.
So I will get this as, if I subtract this, I will get this as minus mgl by 4. That is work done by gravity. So work done by the external agent will be negative of this. So it will be mgl by 4 with a positive sign. Do we understand this? How we have done this? Everyone understand this?
Yes, sir.
Well done. If you are able to do this, I hope it was visible to all of you. Yes or no?
Yes, sir. It's visible.
Okay. This is how we can find out the work done by any conservative force. Okay. Have you noted it down?
Done, sir.
So next heading that is going to come is relation between conservative force and potential energy. Relation between conservative force and potential energy, and we'll straight away write the relation. Conservative force F vector is minus of del u by del x into I plus del u by del y of j plus del u by del z times k. You understand the meaning of this del?
Yes, sir.
This del is known as partial derivative.
Partial. Yes, sir.
This del is known as your partial derivative. One more thing that you must understand is sometimes we have a one-dimensional force, so it is only along x-axis or only along y-axis. Then you can have a graph between potential energy and your x. So this is only for one-dimensional force. Do we understand this? Now this graph is drawn between potential energy and x. And there are certain points that you can see, point P, point Q, point R. Now to find out the force on this particle, what do you do? Since it is only force along x-axis, we can write it as minus del u by del x. Okay, do we get this? Yes or no?
Yes, sir.
Now at point P and R, we have minimum potential energy. Do we understand this?
Yes, sir.
At point P and R, we have minimum potential energy. And these are the points of stable equilibrium. Have you heard about stable equilibrium?
Stable.
These are the points of stable equilibrium. At point Q,
Potential
we
energy
have
maximum.
maximum potential energy, and this is the point of unstable equilibrium. Do we understand this? Yes or no?
Yes, sir.
So these are the things that you must remember. These are known as points of equilibrium. I'll give you 2 minutes to note this down. In the next class, we will move ahead and understand more things about this points of equilibrium and equilibrium of a particle in detail. We will not be able to cover it in this class because the time is not there. So we will cover it in the next class with the points of equilibrium. What are these points of equilibrium? And then we'll move on to something known as law of conservation of mechanical energy. I'll give you 2 minutes, note this down.
Done, sir.
Everyone got this?
Yes, sir.
The potential energy curve. We will again come to this curve in the next class and see what all things we can find out from this curve. I've sent you the sheet. You please find out whether the sheet has been received at the office and ask them to give you a copy of that sheet. And I would ask you to solve questions of that sheet. We will be covering, we will be done with your work, power, and energy probably by not tomorrow, but maybe by Monday we will be able to finish this point, this chapter. So you will get a Sunday in between, solve as many problems as you can. One of those problems is going to come in your JEE, I'm sure. So I'll wind up this class here, and if you have any doubts, come up. From my side, the class is over. We have done quite a bit in today's class. We have covered what is conservative force. We have found out the work done by the conservative force is negative of change in potential energy. We'll do more questions on this in the next class. So till then, take care. Have a good day and God bless you all.
Thank you, sir.
Bye, beta. Take care.
Bye, sir.